I want to move on and talk about this quantum physics idea of light. Around 1905, there's this fella, um, what's his name again? Einstein. And he developed, there's this other fella, Planck, who had some ideas about quantum physics. Now, Einstein wasn't necessarily all in on this quantum physics thing, and you can read some side things about that or watch some YouTube videos about how Einstein wasn't necessarily on board totally with Planck. But around 1906, he and Planck were doing some things simultaneously that developed this idea of quantum physics. And that energy for quantum physics is quantized. Now, when I say quantized, quantum energy or quantized energy, the word quanta, Latin, means countable. Quantity, we know this, right? Quantity is the word that we use in English. But quanta are individual nuggets of light and wave energy. And so we call these individual nuggets, when it comes to light, photons. They're countable, they're quantized, they're packages. And they needed to use this idea of quantized energy to explain the photoelectric effect. So there's electromagnetic radiation is emitted in bursts, and these bursts of energy are called photons, these nuggets. And if you like, these nuggets have wave properties, yeah, but they fly through space as packets. So we can talk about light as having a wave property, but it's also a localized, which means nuggetish kind of energy thing that travels through space. Energy packets. Okay. Now the wild thing is, and this is something I'm not going to touch on just now, but these nuggets, we're forced to think of them as taking up a small amount of space, but they have frequencies and wavelengths where the wavelengths can actually be quite long in the case of radio waves, but we still think about individual nuggets of photon energy as being quite small, collapsed into a small locale. So, oh my goodness, this is a hard thing for the human brain to wrap its head around, and that's why we have names like Einstein and Planck in the conversation. You know, the big minds, right? And so people make a whole career out of truly understanding this stuff. And the energy of a photon is given by E equals hf. Now, this h value, this is actually called Planck's constant, and f is the frequency of the radiation. And H is Planck's constant, or I believe you'd say his own last name is Planck. I'm just so committed to the anglicization, sadly. But Planck's constant. Now, we know that the higher frequency the radiation is, the higher the energy. And if you want to prove that higher frequency is higher energy, take a skipping rope. Wiggle it slow at a low frequency. It doesn't take much energy. Take a skipping rope, wiggle it fast. It takes a lot of energy, right? This is a very kinesthetic way of talking about waves. When you're making a wave on a skipping rope, high frequency waves are high energy. And this carries to be true for photons as well. Now, we know from our studies of sound that speed for a wave is equal to lambda times frequency. And so it stands to reason that for light, the speed of light, c, is equal to the frequency times the wavelength of light. This is the universal wave equation. It's not just true for sound waves, it's also true for water waves, it's also true for light waves, right? So if we know the speed of light and we know the frequency of light, then we can calculate the wavelength of said light, right?
So that v is velocity.
That this v is velocity, this c is specifically the speed of light as a velocity, and we usually would think of it as the speed of light in a vacuum, 3.00 times 10 to the power of 8 meters per second, unless we're told otherwise, 300 million meters per second. And I forgot to sort of say it out loud, but Planck's constant is 2.6 times 10 to the power of negative 34 joule seconds. But if we wanted to express that in electron volts, remember I mentioned electron volts earlier, this is actually a nice little conversion here. 1 electron volt is equal to 1.60 times 10 to the power of negative 19 joules. Okay, so that's a nice thing to know if I ever had to convert between electron volts and joules, which at some point you're going to have to, okay? I already got somebody looking up what the charge of an electron is and recognizing that 1.60 figures into the charge of an electron. So yeah, there's a connection there. Okay. So, but velocity of light, we say, is frequency times wavelength, which we just put as a equation up above. And if we rearrange that, then we end up getting frequency equals the speed of light divided by wavelength. And then we just said, you can call this equation 1 if you want, but equation 2 would be E equals HF. And if we sub equation 1 into equation 2, then we get this equation here, HC over lambda. And the reason we care about that is that this would be the way to calculate the energy for an individual photon if you knew its wavelength, whereas this would be the energy for an individual photon if you knew its frequency. We're just relating the two together, okay? It depends on what you know. And if we were going to do some coloring here, now I don't have the best colors for this, but let's just say that red light, let's make, do I have a red marker? Yeah, I guess I have a red marker. Red light would be the stuff at this end of the visible spectrum. And I don't know if I have purple, so maybe I'm going to take like a blue highlighter and a pink highlighter and hope that you believe that that's purple now. Okay, so we got purple at that end of the visible spectrum. And so if this is, between purple and red is the visible spectrum, the rainbow as we call it, we have the color spectrum, Roy G. Biv, which when I was a kid, I was told that Roy G. Biv was a leprechaun that lives at the end of the rainbow, and his name is Roy G. Biv. It's just a way to remember the color spectrum. But red, orange, yellow, green, blue, indigo, violet. Okay? All right, so we get down to violet down at this end. And if this is violet, then anything beyond violet is ultraviolet. Beyond violet, it's ultra. Anything beyond red is infrared, beneath the red. Okay? So we say that if this is red and this is violet, we got infrared and ultraviolet, but these guys are lower energy because we have lower frequency. But it also means that we have longer wavelengths. So longer waves. These guys here, I've got wavelengths for UV light less than 400 nanometers. These guys are the higher frequency and longer. Oh, sorry, I said that wrong. Higher frequency and shorter wavelengths, shorter lambdas. So just trying to tie it to the rainbow because that helps people just a little bit sometimes to visualize what's going on here in terms of a chart. But we're talking about the photons being sufficiently localized. And I tried to use that word earlier when I was talking about photons, sufficiently localized. And what that means is, this is the language of the scientists themselves, it means that photons are super small. They're packed into a little nugget. They're sufficiently localized so that the whole quantum of energy and I'm going to call that nugget of light energy. This is just me trying to use street language to talk quantum physics. That whole nugget of light energy for an individual photon, HF.
What does that word say? Like under.
Super small?
No, like nugget of light.
Quantum. The whole countable bundle of energy is a little nugget of energy. Remember, I drew some little photon cartoons up here? Each one of those is a little quanta of light energy, bundled up and packaged for us. And this is the individual energy. So for an individual photon, its frequency times the Planck's constant can be absorbed because it's just a little nugget, kind of like my BB gun from earlier, absorbed by a single electron, much like a single BB gun pellet could smack into a single piece of Lego if I was trying to shoot pieces of Lego off as opposed to trying to shoot electrons off of a piece of metal, you know? So the electron can either share its excess energy when it gets hit by this photon with the other electrons surrounding it, and the ion lattice. You probably have talked about ion lattices when you're in chemistry class. Or, and this is key because this is what we're talking about right now, it can use the excess energy to eject an electron. Oops, space too small. To eject an electron out of the metal. And that's what we were kind of talking about here, these photoelectric ejections. So because of the interaction of this electron with other atoms, it requires a certain minimum energy to escape the metal surface. Now, I know that when you're in chemistry class at a senior level, you've talked about ionization. And it takes a certain activation energy, a certain minimum amount of energy to ionize an atom. Agreed? You got to achieve that certain threshold before the electron will get popped off of the home atom. True? This is a very similar idea. We're trying to get an electron to get ripped off of a piece of metal, and so we have to have at least the right amount of energy to rip that electron off. Anything less than that won't rip it off. Remember we were talking about the frequencies for these incoming photons? If you don't have enough energy associated with this incoming photon, then you're not going to knock an electron off. All cool? Right? So BB guns versus air rifles, I suppose, if we want to go back to that. But the minimum energy required to escape, and when I say escape, let's call it the home atom, depends on the metal. So each metal has a different amount of energy that's required to rip electrons off of it. You know, potassium is going to require one. Lithium will require another one. Really depends on how strongly they hold on to their electrons. Again, talk to your chemistry teacher about that one, about how some metals hold on to their electrons tighter than others. But we can accept that, okay. It depends on the metal and the amount of energy that you have to overcome to rip off an electron. Unlike in chemistry class where we call it the ionization energy, in this context, we call it the work function. Okay, so it's called the work function. How much work, oops, how did I just spell the work function wrong? My mind wanders. The work function is the amount of energy it takes to rip off an electron. So I'll say it out loud again. The minimum energy required to escape, when I say escape the home atom from which the electron's getting ripped off, depends on the metal. You know, is it lithium? Is it potassium? Is it whatever? And that amount of energy that it takes to rip off that electron is called the work function. If your photon doesn't have at least the same amount of energy as the work function, it's not going to be powerful enough to rip off an electron. Okay? And this is the work function variable. And that work function is the minimum energy for ejecting an electron. And the work function is going to be specific to the type of metal that we're ripping electrons off of. Okay. So for electron emission, the photon's energy, that is the incoming photon, the photon that's about to knock off an electron, has to be greater than the work function. And if I wanted to write this as an inequality, I could write energy for a photon got to be greater than W, the work function. And if the energy for a photon is Planck's constant times the frequency of that photon, we're saying that the incoming photon that's about to smack into the, let's just say potassium, has to be greater than the work function for potassium. Again, all good? I recognize this is high level stuff, so I'm trying to make sure that this is very conversational and like street language. Okay.